There's a question I need help with here. 1.2.1. Without solving for x, show that the solution lies in the interval 2 to 4. We're going to do that question. Let's start by doing 1.1.1. So 1.1.1, we are solving for x. We have 2x multiplied by 3x plus 4 being equals to 0. We have two numbers multiplying each other, right? And then the answer is 0. So 1 between the two numbers need to be equals to 0 itself. That is the only way that is possible. So we have 2x is equals to 0, or 3x plus 4 is equals to 0. Should be easy to see that x is equals to 0, or x is equals to minus 4 over 3. There we go. Other people will multiply out here at this step, which is completely unnecessary. They multiply out and they take a common factor. Why would you do that? Just solve the equation from the get-go. That is 1.1.1. Take a look at 1.1.2. We're supposed to solve 2x squared minus 4x is equals to minus 1. Correct to two decimal places. We know that we are supposed to use the quadratic formula as soon as we see correct to two decimal places. I'm quite convinced that we all know how to do that by now. So let's jump straight to 1.1.3. In 1.1.3, we have an inequality. We have x minus 2 everything squared being greater or equals to 1. Let's expand x minus 1 everything to the power 2. We get x squared minus 4x plus 4 greater or equals to 1. And our critical values, x squared minus 4x plus 3 is equals to 0. In factorizing this, we're going to get x minus 3 multiplied by x minus 1. This is equals to 0. When you multiply out, you go back to x squared minus 4x plus 3. So x is equals to 3 or x is equals to 1. Those are our critical values. As soon as we get to this point, we have two possible sets of solutions. Let me show you what I'm talking about. It's either x, this is the first possible solution. It's either x lies between 1 or we have, or equals to, right? It's either x lies between 1 and 3, right? Or x is less than 1 or x is greater than 3. One between these is the correct answer. We just need to perform a test and see which one it is. But let's take a look at this. Here we're seeing that x lies between 1 and 3. Which whole number lies between 1 and 3? 2 lies between 1 and 3. So let's substitute 2 in our equation and see if our equation is going to be satisfied. If our equation is satisfied, then we're going to know that that first option is our answer. Okay, let's take a look. We're going to have 2 minus 2 squared being greater or equals to 1. Obviously, this is 0. Is 0 greater or equals to 1? No, it is not. So that first option is not correct. Without even testing the second option, we already know that it is the correct answer. But let's just go ahead and test it out for the sake of clarity. Well, we're saying that x is less than 1 or x is greater than 3. Let's take a number less than 1. A number less than 1 is 0. So take a look at this. We're going to have 0 minus 2 squared being greater or equals to 1. Obviously, 4 is greater or equals to 1. Our equation is satisfied, our inequality, I mean. And then now let's take a number greater than 3. Let's take 4. If we take 4, we get 4 minus 2 squared being greater or equals to 1. Obviously, this is going to be 4 greater or equals to 1. Again, our equation, our inequality is satisfied. So we know that x is less than 1 or x is greater or equals to 3. And there we go. We have our answer to 1.1.3. And then now comes the question I want you guys to help me with. Take a look at 1.2. 1.2 says we're given an equation, square root of x minus 2 is equals to 4 minus x. And the question is saying, without solving for x, show that the solution lies in the interval 2 to 4. Right, without solving the equation. Let's show that. Okay, so let's take a look at this interval, 2 to 4. Well, the whole numbers we have is 2, 3, and 4. So let's test these three whole numbers, 2, 3, and 4, and see if that equation is satisfied, starting with 4. Well, let's start with 2. X is equals to 2. When we have x being equals to 2, we're going to have square root of 0. So, square root of 2 minus 2. So, square root of 0, that gives us 0. So, we have 0 being equals to 4. We know this not to be correct, right? And now let's test x is equals to 3. Right, yes, x is equals to 3. Let's see. So, we're going to have 3 minus 1, which is 1. Square root of 1 is 1. And then this is equals to 4 minus 3, which is 1. X is equals to 3. It's okay. It works. Now let's take a look at x is equals to 4. Right. So x is equals to 4. When x is equals to 4, we're going to have 4 minus 2, which is 2. Square root of 2 is square root of 2. And then on the other side, we're going to have 4 minus 4, which is 0. And we know that these two are not correct. So, how are we then supposed to show that the solution lies in that interval? I'm thinking that in the setting of the equation, this or equals to is a mistake. It is not supposed to be there, because if it is not there and we just substitute 3, the two sides will be equal to each other. But then for the mere fact that you are including 2 and 4 and clearly the answers don't make sense, I don't know what is going on here. So those are the two options. Is a typing error, or I'm making a very serious mistake? There's something I can't see, which I doubt is the case. Let me know in the comments. How do you do 1.2.1? I'm interested in your answer. Right. So that is 1.2.1. What about 1.2.2? Can we actually solve the equation? I think we can. Square root of x minus 2 being equals to 4 minus x. Let's go with both sides. We're going to get x minus 2 being equals to 4 squared is 16. And then minus x multiplied by 4 is minus 4x. You multiply the 2. You multiply that by 2, you get minus 8x plus x squared. Okay, so let's take a look. We're going to have x squared minus 9x plus 18 being equals to what? Being equals to 0. Right, so let me just make sure that I'm not making a mistake. 4 squared is 16 minus 8x, x squared. That's fine. And then x squared, this, when it goes to the other side, it becomes minus. So we have minus 8x, and then this becomes positive. So we have plus 18. Okay, it seems like I've solved that. I have not made any mistake. So let's carry on. We need to factorize. Okay, so let's take a look. We have x, and this is equals to 0. 2 factors of 18, when we get minus, when we add, we get minus 9. Okay, minus 6 and minus 3. I think those two work. Minus 6 multiplied by minus 3 will give you plus 18, but we'll add to minus 9. So, right, minus 6 minus 3. So, x is equals to 6 or x is equals to 3. Okay, most of the time, one of the answers turns out to not be correct when you substitute it back in the equation. So, let's see. Let's substitute x is equals to 6. When you substitute x is equals to 6, we're going to have 6 minus 2, which is 4. And then on the other side, we're going to have 4 minus 6, which is minus 2. And then 2 is equals to minus 2. Okay, x is equals to 6 is not a solution to this equation. So this is not fine. Let's substitute x is equals to 3. When I have 3 minus 1, square root of 1 is 1. And then, okay, we are good to go. There we go. Yeah, so that is 1.2.2. Let's do 1.3 and 1.4 on a separate question. But let me know in the comments, how did you solve 1.2.1? Which video do you want me to do next? Which question? Question 2, question 3? Looks interesting? Let me know in the comments. Let's take a look at 1.4. 1.4 is quite an interesting question. We don't usually come across something like this. Well, the last question on question 1, solving for x, it's always interesting, right? But let's take a look at the case we have. We have r plus 2s being equals to a, and r minus 2s being equals to b. And we're supposed to prove that r multiplied by s is equals to a squared minus b squared divided by 8. How can we possibly do that? Well, it's either you realize it or you don't, but I hope you did realize when you were answering that question, this question, that we have a difference of 2 squares right here. A squared minus b squared. This is a difference of 2 squares because we know that a squared minus b squared is equals to a plus b multiplied by a minus b. There we go. That is the key to answering this question. Well, maybe another person can probably introduce another possible way, but as soon as you realize that you have a difference of 2 squares, it should be fairly easy. Let me show you what I'm talking about. So because we have a difference of 2 squares, let's take a look at a plus b and figure out what this is equals to. A plus b, we know that a is equals to r plus 2s, right? So we're going to have r plus 2s. And then plus b. b is r minus 2s. So r plus r is 2r. So we have a plus b being equals to 2r. rs minus, not rs, but 2s minus 2s will give us 0. So there we go. We have a plus b, which is equals to 2r. Right. And then now let's figure out what a minus b is equals to. Right. And then this is going to be r plus 2s minus r minus 2s. So let's take a look. A minus b will be equals to r minus r will give us 0. And then 2s minus minus 2s will give us 4s. So there we go. We have a plus b, which is equals to 2r. And then we have a minus b, which is equals to 4s. If in this equation we make r the subject of the formula, we get a plus b divided by 2 being equals to r. And then in this equation, if we make s the subject of the formula, we get a minus b divided by 4 being equals to s. So r multiplied by s will be equals to a plus b over 2 multiplied by a minus b over 4. Well, it should be easy to see that in the numerator we have a plus b multiplied by a minus b, and then on the denominator we have 2 multiplied by 4, which is 8. But there what we have on the numerator is a difference of 2 squares. So this is a squared minus b squared over 8. Determine a simplified expression for Tn. Well, let's just determine Tn. I don't think simplified expression is really necessary. Too wordy for my liking. But either way, 2.1.1, we want Tn for an arithmetic sequence. Obviously, we're going to have a plus n minus 1 multiplied by d, where a is the first term. It happens to be 85. There we go. And then d is the common difference. We can find d by saying tn minus tn minus 1, the difference between two consecutive terms. So we can say 76 is t4, 1, 2, 3, 4. So we can say 76 minus 79. This is equals to minus 3. Right, the difference between two consecutive terms. So Tn will be equals to a is 85, plus n minus 1 multiplied by d. What is d? d is minus 3. Well, we can further simplify this and make it a simplified expression. So Tn will be equals to 85. N multiplied by minus 3, so minus 3n, and then minus 1 multiplied by minus 3, that is plus 3. So we have minus 3n plus 88. Let me substitute a few values of n and see if I'm happy with the answers. So minus 3 multiplied by 1 plus 88 is 85. Minus 3 multiplied by 2 plus 88 is 82. And then minus 3 multiplied by 4 plus 88 is 76. So think I'm happy with the simplified expression for Tn. That is 2.1.1. Let's go ahead and take a look at 2.1.2. Right, let's see what's happening here. Which term will be the first negative number in the sequence? Which term will be the first negative number in the sequence? Most of these math problems, you're solving for x, you're solving for n, you're solving for y. The equation, the task is in setting up an equation you need to solve. So let's take a look at this one. Which term will be the first negative number in the sequence? Okay, we know that Tn is equals to minus 3n plus 88. So which term will be the first negative number? So we are looking for minus 3n plus 88 to be less than 0. In doing this, we will easily find the value of n for which the terms will be negative. The term will be negative. So let's go ahead and do that. Minus 3n is less than minus 88. We divide both sides by minus 1. When we do that, the inequality changes, right? So we have 3n being greater than 88. You just need to think about this for 30 seconds, and then you will realize that if we divide by minus 1, the inequality must change. And then when we divide by 3, on both sides, we get n being greater than 88 over 3. 88 over 3 is about 29.33. I just put that in my calculator. It's about 29.33. So when n is greater than 29.33, then we're going to have a negative number in the sequence. So the first value of n should be equal to 30 for us to get a negative number in the sequence, because we cannot take 29.33 as it is, because n is the position of the term, and then we don't have a position with a decimal, right? We have to round it off. So when n is equal to 30, that is where we have our first negative term. 2.1.2. Let's take a look at 2.2. Okay, a quadratic sequence with the general term Tn has the following properties. We have T11 being equals to 190, and then Tn minus Tn minus 1 is equals to 4n minus 3 when n is greater or equals to 2. There's something you need to realize about this statement. Tn minus 1 is the terms in the first difference of the quadratic sequence, which gives us the arithmetic. Okay, and then the equation itself is saying determine the first term of the quadratic sequence. Let's take a look. Tn is equals to an squared plus bn plus c. We want to find the first term. So T1 is equals to a plus b plus c. This establishes the task we have in hand. We need to find a, b, and c. So how can we go about that? Let's take a look at T11. T11 is equals to 190. But in terms of Tn, we're going to have a multiplied by 11 squared plus b multiplied by 11 plus c being equals to 190. So what is 11 squared? We know that to be 121. So we're going to have 121a plus 11b plus c being equals to 190. So clearly we can't do anything amazing with that piece of information. We need to find another way to generate more information because we are not given a lot. The information we have, the only other thing that we are yet to use is this statement here. Tn minus 1 is equals to 4n minus 3 when n is greater or equals to 2. So let's go ahead and use that. Like we have established, that is the difference of the terms in the quadratic sequence. So let's generalize, okay? So in some quadratic sequence, we're gonna have T1, T2, and T3, of which we can find the difference of these terms and have a arithmetic sequence, because the difference of a quadratic gives you arithmetic. So let's go ahead and do this and see what we have. T1, we've already established that T1 is A plus B plus C. But what about T2? Let's not forget that Tn is equals to an squared plus bn plus c. T2 will be equals to 4a, right, n squared, 4a plus 2b plus c, okay? And then T3 will be 9a plus 3b plus c. There we go. That is T1, T2, and T3 of a quadratic sequence in general. Okay, let's find the difference between these two. In finding the difference between those two, we get 3a plus b. This is why you equate 3a plus b to the first term of, the difference between T2 and T1 in a quadratic sequence. In other cases where you are solving for an squared plus bn plus c. Right, and then the difference between T3 and T2, we're going to have 9a minus 4a, which is 5a. 3b minus 2b, that is plus b. C minus c is 0. Okay, there we go. We are making progress. But there's something special about these. Mind you, these right here. Well, I just made a mistake there. Let me go back there. Yeah, this right here, 3a plus b. This is T2 minus T1 of the quadratic sequence, right? And what do we have here on the left-hand side? We know that Tn minus 1 is equals to 4n minus 3. Okay, so that allows us to say that 3a plus b is equals to 4n minus 3. So this is the difference between T2 and T1. So we're going to have 4 multiplied by 2, which is 8 minus 3 is equals to 5. Okay, and then this right here is the difference between T3 and T2. So we're going to have 5a plus b being equals to 4 multiplied by 3, 12, minus 3, 9. So there we go. We have these two equations. With these two equations, we can solve for a and b, but we still need to solve for c. Let's go ahead and solve for a and b. In solving for a and b, we can make b the subject of the formula here and get 5 minus 3a, and then substitute it into this equation. We're going to get 5a plus 5 minus 3a being equals to 9. So 2a is equals to 4, a is equals to 2. 5a minus 3a, that is 2a, 9 minus 5 is 4. No mistake there. I think we're good to go. And then b, on the other hand, 5 minus 3 multiplied by a. A happens to be 2. So 5 minus 6, that is minus 1. So b is equals to minus 1. A is equals to 2, b is equals to minus 1. We need c. In order to find c, we're going to use T11. We're going to come back here to this equation here. Because now we have a, we have b, we just need c. So a is equals to 2, b is equals to minus 1, and 121a plus 11b plus c is equals to 190. So 121 multiplied by 2 plus 11 multiplied by minus 1 plus c is equals to 190. So, okay, 121 multiplied by 2 minus 11. Just minus 11. So we get 231 plus c is equals to 190. So c is equals to 190 minus 231. We get minus 41. So T1 will be equals to, well, let me not say T1. but Tn will be equals to, I want to determine Tn because I will use it to see if I get T11 is equals to 190. Tn is going to be A is 2, N squared, B is minus 1, so minus N, A squared plus B n plus C, and then C is 41. So T1 is going to be equals to 2 multiplied by 1 squared minus 1 minus 41. Let me put that in my calculator. 2 minus 1 minus 41 essentially. So this is minus 40. That is the value of T1. But let me check T11 and see if I get 190. So 211 squared minus 11 minus 41. Okay, so 2 multiplied by 11 squared minus 11 minus 41, I'm getting 190. So I'm a bit confident that we have solved this system of equations correctly. So that is 2.2. Let me know in the comments, did you manage to figure this one out, or did you use a different approach and got to the same answer? Let's talk in the comments. For which values of x will this sum exist? What is special about this sum? We are going from k is equals to 1 to infinity. We can only calculate the sum of infinity terms if the sum is convergent. Because if it is divergent, then we can't calculate the sum to infinity because it keeps on increasing. But if it is divergent, then we can calculate the sum to infinity. So let's take a look. We have 4x minus 1 being equals to k. The first term here, when we substitute k is equals to 1, we're going to have 4x minus 1. So that is a. And then when you substitute k is equals to 2, we're going to have 4x minus 1 to the power 2. And then after that, obviously, we're going to have 4x minus 1 to the power 3. So on and so on. So we can see that the common ratio here is 4x minus 1. If you divide 4x minus 1 to the power 2 by 4x minus 1, you get 4x minus 1. So the common ratio here is 4x minus 1. And we're saying that for these to exist, the sum from k is equals to 1 to k to infinity, we need the ratio to be between minus 1 and plus 1. We add plus 1 on both sides, we get 0. 4x less than 2. We have just added plus 1 on all the sides. Right. So let's go ahead and divide both sides by 4. 0 divided by 4, that is 0. And then 2 divided by 4 is 1 over 2. So when x is between 0 and a half, this sum will exist, right? Because r will be between minus 1 and 1. The sum, or not the sum, but the series will be convergent. So there we go. That is 3.1. And then 3.2, on the other hand, let's hear the stories. The figure below shows a pattern of 5 circles touching externally, whose centers lie on a straight line of length L units. The radius of these circles form a geometric pattern, where the radius of the smaller circle, well, the first circle, let's go ahead and make sense of our information, is 3 units. So for the first circle, let's say we have circles 1, okay, let me zoom in. 1, 2, 3, 4, 5. So that is T1, T2, T3, T4, T5. Right, so the radius of the first circle is 3 units. So we have R being equals to 3. And that of the fifth, the largest circle, is 48 units. Right, so R1 is equals to 3. And let's take the radiuses as our terms actually. Okay, if we were to do that, we'll see that T1 is equals to 3. And the fifth circle, T5, is equals to 48. Okay, and what are we looking for? We are looking for the common ratio. So let's go ahead and the common ratio of the geometric pattern formed by the radii of the circles. Okay, so R is equals to T2 divided by T1. But here we have T1 and T5. But that's not a problem. Let me show you why. We just need to stick to the basics. We know that A is equals to T1, right? So A will be equals to 3. And then T5 is AR to the power 4. And this is equals to 48. So this is what we have. We don't need to panic. We can just substitute A into T5. We're going to have 3 multiplied by R to the power 4 being equals to 48. So 48 divided by 3, R to the power 4 is equals to 16. So we need a number that multiplies itself 4 times and give us 16. That is 2. So R to the 4 is equals to 2 to the 4. So R is equals to 2. So there we go. That is our common ratio, 3.2.1. And then now 3.2.2, we want to determine the value of L. Determine the value of L. So L is made up of the radiuses of the circles, right? Okay, but take a look at something. We have L will be the diameter of the first circle plus the diameter of the second circle plus the diameter of the third, right? And then the diameter is just equals to 2R. So we can just calculate the sums of the radiuses of the 5 circles and multiply that by 2. Okay, take a look at this. We know that A is equals to, 3.22. We know that 3.2.2, A is equals to 3 and R is equals to 2. So we can calculate the sum with these two variables, right? Let's see, S5, the sum of the first 5 circles will be, how do we calculate the sum of the sum when we are given a geometric series that is finite? I think it is A R to the n minus 1 divided by R minus 1. Okay, let me just verify this before I make any silly mistake. I think this is one of the very few times I actually verify formula. Okay, it is correct, no issues. So let's carry on and solve that. Okay, we are back here. So A is S5, A is 3, R is 2, the number of terms is 5 minus 1 divided by 2 minus 1. Okay, so let's take a look. We have 3 to the power, well, not 3 to the power, 3 multiplied by 2 to the power 5, minus 1 divided by 2 minus 1. This is 93. We can actually do this manually also and see if it is correct. We can actually do this manually instead of using an equation, right? So that is 3.2.2. We're not done because this is the sum of the radiuses, and we are seeing that the diameter is equals to 2R because L is the sum of the diameters. So D will be equals to 2 multiplied by S5. This is the sum of the radiuses, and we are looking for 2 times that. That is what L represents, the diameter of the circles. So we're going to have 2 multiplied by 93. Is that 186? There we go. D, not D, but L. Please forgive me for that. So L is equals to 186 units. We don't know which units we are using here, but L is equals to 186 units. I think we are quite happy with that. We can move to what? We can move to the equation that follows. So let's go ahead and take a look. 3.2.3, the pattern is extended by 5 more circles to 10 circles. Calculate in terms of pi the total area of the circles of the 10 circles of the new pattern. Okay, so now we no longer have 5, but we have 10. But what is the equation for an area of a circle? Well, the area is equals to pi r squared, and we are looking for the area of the the first 10 circles. So how can we go about that? Well, the total area. So let's say that the total area will be equals to the area of the first circle plus the area of the second circle up until the area of the last circle. I think we can all agree on that. That is easy to see. Well, area is pi r squared. What am I saying there? Right. So area of first circle plus area of second circle up until the area of the 10th circle. Right. But we know that area is pi r squared. So the total area will be pi r squared plus pi r squared plus up until the last cycle, pi r squared once more. So the total area, right, we can take pi as a common factor because pi is going to be the same. And then we have r squared, the first cycle, plus r squared, the second cycle, up until the last cycle, which is, we're going to have another r squared. So can we actually find the answer to this using an equation? Can we actually do that? Let me take a look at the mark location. The mark location is 4. Think about it. Can you actually find r squared plus r squared up until the last cycle using one equation? Obviously, we can do it manually, right? But I'm just wondering if we can do it using an equation. Well, I'm not sure we can, but you know, if you can think of a way, then you should definitely try that out. So this is what I'm gonna do. Instead, I'm gonna say pi, and then I'm gonna do everything manually, right? Because I cannot find a obvious way to do it. So right, we know that the radius of the first term is of the first cycle is 3 units. So we're gonna have 3 units squared plus the radius of the second cycle. What was that? The radius of the second cycle. So we know that a is 3 and r is 2. So we have 2 to the power 1 if it is the second cycle. So 2 to the power 1, we get 6 squared. So let's have that there. So we have 6 squared plus 2 to the power 2, that is 12. So we have plus 12 squared plus 2 to the power 3, that is 24 squared. I think I can just carry on. We can see the pattern here. 24 multiplied by 2 is 48. 48 squared. And then multiply that by 2 again. 96 squared by 2. 192 squared. And then by 2 again. Let me make sure that I don't have more than 10 terms. So this is 1, 2, 3, 4, 5, 6, 7. Okay, if you multiply that by 2 again, you have 384. So 384 to the power 2, that is the 8th term. Again, 768 to the power 2, and the last term, 1536 to the power 2. So I just need to put this in my calculator. Okay, so I'm getting, is this 3 million? 3,145,725 pi units squared as the total area of the 10 circles. There we go. We have a function g of x, which is equals to minus 4 over x plus p plus q. There we go. And then we're given the axis of symmetry. Y is equals to x plus 1 and y is equals to minus x plus 3. We're supposed to find the value of p and the value of q. Well, we're supposed to show that p is equals to minus 1 and q is equals to 2. So there's some basics that you need to recall in order to answer these questions. These lines of axis of symmetry, they touch at a point where we have minus p as the x coordinate and q as the y coordinate. So in order to find this minus p, we can just equate these axes of symmetry. We're going to have x plus 1 being equals to minus x plus 3. So 2x is equals to 2. X is equals to 1. We're dividing by 2 on both sides. But what are we saying? We are saying that when at minus p, That's where these two lines touch. So let's take a look. We're going to have minus p being equals to 1, because when x is equals to minus p, that's where they touch. So clearly, p should be equals to minus 1. So there we go. We have the value of p. And then the value of q, we can just substitute into one of the x's of symmetry. If we substitute on x plus 1, we have 1 plus 1, which is equals to 2. And then on the other equation, we get the same thing. We get minus, minus p. So we're going to get minus 1 plus 3, and this is equals to 2. So there we go. The value of p is minus 1, and the value of q is 2. So now we know that g of x is equals to minus 4 divided by, let's take a look, x minus 1 plus 2. Let's take a look at the equation that follows. 4.2. We're supposed to calculate the x-intercept of g. So x-intercept, we let y be equals to 0. We're going to get 0 being equals to minus 4 divided by x minus 1 plus 2. If we take 2 to the left hand side, we get minus 2 is equals to minus 4 divided by x minus 1. Let's cross multiply. We're going to get minus 2x plus 2 is equals to minus 4. So minus 2x will be equals to minus 4 minus 2. Minus 4 minus 2 will give us minus 6. And then we divide both sides by minus 2. So x is going to be equals to 3. So there we go. That is the x-intercept. Right. And then 4.3, we're supposed to sketch the graph of g and show the asymptotes and the intercepts. Okay, let's gather our variables and sketch therefore. So x-intercept, we know the coordinates. X is 3 and y is 0. But what about the y-intercept? What about the y-intercept? Let's take a look. If we were to substitute 0 there, we would get minus 4 divided by minus 1, which is 4, plus 2 is 6. So y-intercept, we have 6 and 0. Now we just need the asymptotes. Well, we know that q is equals to 2. So our vertical, not our vertical, but our horizontal asymptote y is equals to 2. And then what about the vertical asymptote? X cannot be equals to 1. We can clearly see that x cannot be equals to 1 because we're going to have 0, which gives us undefined. So x is equals to 1 is our vertical asymptote. Now we can sketch. We need our axis. So the y-axis and the x-axis. There we go. And then this is the y and this is the x. We need our asymptotes. We have an asymptote x is equals to 1. So right here we have an asymptote. So there we go. And then another one, x is equals to 2. So somewhere here we have an asymptote. And then we just need to place our intercepts now. We have an intercept when x is equals to 3. So if this is 1, then 3 should be somewhere here. So there we have our intercept, not asymptote. And then when y is equals to 6, here we have another intercept. So how is our graph going to look like? Something like this, right? And then there we go. I think we're good to go here. Yeah, we have the sketch of G. 4.4, for which values of x is G of x greater than 0. Okay, let's take a look. So here we have x is equals to 1, right? When x is less than 1, G of x is greater than 0. We can clearly see that from the sketch. Here, G of x is greater than 0 when x is less than 1. And then when x is greater than 1, well, from here up to x is equals to 3, G of x is equals to 0 or less than 0. But when x is greater than 3, so from this point up to infinity, clearly g of x will be greater than 0. So there we go. We have two functions, g of x and f of x. A and c are the x-intercepts of f, where b is the y-intercept and d is the turning point. The two functions, g of x and f of x, they touch each other at the point d, which is the turning point of f. And then the first equation, 5.1.1, determine the length AC. Like we've already said, A and C are the x-intercepts of f of x. So before we can even get to calculating the length of AC, let's determine the x-coordinates at A and C. Okay, so we have f of x, which is equals to minus x minus 2 squared plus 9. So f of x is equals to, so let's solve this, x minus 2, everything to the power 2. We're going to have x squared minus 4x plus 4, and then plus 9. Let's multiply out by the minus sign. If we do that, we're going to get f of x being equals to minus x squared plus 4x minus 4 plus 9. So f of x is equals to minus x squared plus 4x. And then what is minus 4 plus 9? That is plus 5. So there we go. We have f of x. Now we can go ahead and determine the x-coordinates of A and C. So we know that these are x-intercepts. So y is equals to 0. So we're going to have minus x squared plus 4x plus 5 being equals to 0. If we divide both sides by minus 1, we get x squared minus 4x minus 5 is equals to 0. So this is what we need to factorize. So factors of minus 5, of which when we add, we get minus 4. That is minus 5 and plus 1. Okay, minus 5 plus 1 is minus 4. And then minus 5 multiplied by plus 1 is minus 5. So x is equals to 5, or x is equals to minus 1. So this is A. A is minus 1 and 0. And then C is 5 and 0. So AC will be equals to, we don't necessarily need to use the distance formula here because they share the same, or well, not the same y value, but at A, y is equals to 0, and at C, y is equals to 0. So we can just say that AC is equals to 5 minus 1. Okay, and this is 6 units. We know that from here to C is 5 units, and then from A to the origin is also 1 unit because A is minus 1. So 1 plus 5 is equals to 6. So I think we have done everything the right way there. So that is 5.1.1. What about 5.1.2? Determine the value of B. B, it's on g of x. We know that g of x is equals to b to the power x. Well, we know that the two functions g of x and f, they touch at d. So if we can determine the coordinates of d, then we can substitute those coordinates of d into g of x and find the value of b. Let me show you how. Okay, we know that f of x is equals to minus x squared plus 4x plus 5. I think I'm more comfortable with this form, right, with that general format compared to this one, right? Okay, so we need the coordinates of d. D is the turning point. So x at the turning point, at least x is equals to minus b divided by 2a. So minus 4 divided by 2 multiplied by minus 1. So 4 divided by 2 is 2. Okay, there we go. And then f of 2. We want to substitute 2 into f of x. So minus 2 squared plus 4 multiplied by 2 plus 5. This is equals to 9. So f of 2 is equals to 9. So this point, when x is equals to 2 and y is equals to 9, it lies on g of x. So we can substitute it into g of x. In doing that, we're going to have 9 is equals to b to the power 2. We want the same exponents so that we can just equate the bases. How do we do that with 9? 3 to the power 2 is equals to b to the power 2. 3 is equals to b. There we go. So g of x is just equals to 3 to the power x. Right. There we go. That is 5.1.2. Then 5.1.3, determine the values of x for which g of x is greater or equals to 9. Well, we don't need to calculate anything here. We can just see here that, take a look at this. When x is equals to 3, g of x is equals to 9. But when x is equals to 4, g of x will be greater than 9. And when x is equals to 2, g of x, well, not 3, this is actually 2, right? When x is equals to 2, g of x is equals to 9. And then when x is equals to 3, g of x will be equals to 27, right? 3 to the power 3. But when x is equals to 1, g of x will be equals to 3. So we can clearly see that g of x is greater or equals to 9 when x is greater or equals to 2. That is our solution. I think we can also solve this one algebraically. Let's see if we can do that. 3 to the power x greater or equals to 9. So 3 to the x greater or equals to 3 to the 2. So when x is greater or equals to 2. Yeah, we can actually do this algebraical. But there we go. That is 5.1.3. 5.1.4. Write down the equation of h if. So this is 5.1.4. If h of x is equals to f of x plus 2 minus 9. Okay, let's do one operation at a time. Let's figure out this part. F of x plus 2. Right. So in place of x, we're just going to substitute x plus 2. That's what that statement means. It means to go to f of x and substitute x plus 2 in place of x. So we're going to have minus, in place of x, x plus 2 minus 2 everything squared plus 9. So this is equals to, so this is f of x plus 2, and this is equals to minus, well, x squared plus 9. So we have taken care of that part. Now let's take care of this part, minus 9. So we're going to have f of x plus 2, and then we just subtract 9. This is equals to minus, this is just x squared, okay, plus 9, and then minus 9, right? The 9 that is here, we are counting for this. We are accounting for that. So f of x plus 2 minus 9 is going to be equals to minus x squared plus 9 minus 9 is 0. So there we go. This is f of x plus 2 minus 9. 5.1.4. Let's take a look at 5.1.5. So 5.1.5, how can the domain of h be restricted so that h inverse will be a function? Well, h of x is equals to minus x squared. So h inverse, we have x being equals to minus y squared, minus x is equals to y squared. So y is equals to the square root of minus x. So in order for this to be a function, we need x to be less or equals to 0. Because when x is equals to 0, we're going to have square root of 0 that is defined. And then when x is equals to, let's say, minus 1, we're going to have minus multiplied by minus 1, which is positive. And that is totally fine. But when x is greater than 0, issues arise. Let's say, for instance, x is equals to 4. We're going to have the square root of minus 4, which is going to give us undefined. So that's what we need. We need x to be equals to or less than 0. 5.1.5. There we go. 5.1.6, let's take a look at what's happening here. We're supposed to show algebraically that g of x plus a half is equals to square root of 3 g of x. Okay, let's see. G of x plus a half. So in place of x, we need to substitute x plus a half. Okay, I think that requires us to use exponential loss. Yes, because this is equals to 3 to the x multiplied by 3 to the half. And the 3 to the half is the same as square root of 3. And then 3 to the x is just g of x. I think we have proved that. Write down the coordinates of A, the x-intercept of f. So we have two functions, f of x and g of x. Well, f of x is equals to log of x and the base is half. And we are looking for A, the x-intercept of f. We know fully well that for the x-intercept, we just need to let y be equals to 0. We're going to get 0 is equals to log of x and the base is half. If we apply one of the log laws, then 1 over 2 to the power 0 should be equals to x. The base just goes and carries the 0. So what is any number to the power 0? The answer is 1. So this is the x value at A. But you're looking for the coordinates of A, not the x value at A. So we can't leave it like that. This is actually not complete. We then have to say that A, the x coordinate is 1 and the y coordinate is 0. Now we have covered all that we need to cover. Let's take a look at 6.2. Determine the domain of f. Well, f, we still have f of x being equals to log of x and then the base is half. The base doesn't really affect us that much. It's this x that we need to pay attention to. For the function f, the domain x is greater than 0. X is greater than 0. That is because log, we can only feed it positive numbers and numbers greater than 0 essentially. We cannot feed it 0 or numbers that are less than. If you put 0 on log, you're going to get undefined. If you put a minus number, you're going to get undefined. So here we need whatever that is in here to be greater than 0. But in our case, we just have x. So x is greater than 0. If, for instance, we had x minus 2, then we would say that we need x minus 2 to be greater than 0. So x needs to be greater than 2. Right, but in our case, we just have x. So that is why we are saying that x is greater than 0. We cannot feed log anything that is less than 0. So there we go. That is the domain of f. 6.3. Determine the equation f inverse in the form y is equals to. Well, here's f of x. Let's just swap x and y in attempt to find the inverse. So the first step in finding an inverse, we swap in x and y. We're going to have x being equals to log of y, the base still a half. And then now we need to make y the subject of the formula. The half is going to carry x. And then we're going to have y being equals to a half to the power x. So there we go. This is the inverse of f of x in the form y is equals to. 6.4, let's go ahead and do that. Sketch the graph f inverse. Indicate on your graph the intercepts with the axis and the coordinates of one other point on the graph. Okay, let's see. So we need the intercept. So let's start with the x-intercept. We let y be equals to 0. So we're going to get 0 being equals to a half to the power x. We know that this is impossible. If you have a half to the power any number, it can never be 0. It can get very close to 0, but it actually never gets to be 0. So there's no x-intercept for y. And then y-intercept, let's see if that exists. We're going to have 0 being equals to a half to the power x. So this is our y-intercept. We're interested in x, and x is up there. So what can we do? We cannot write 0 with the base of half because we have said that that is impossible. So we can introduce, can we introduce log on both sides? Let's see. If we introduce log on both sides, we're going to have log of 0, which can't be true. Well, I'm doing this the wrong way. I'm letting you know why b equals to 0. I'm surprised because issues are arising. Y-intercept, we are supposed to let x be equals to 0, not let y be equals to 0. So any number to the power 0 is 1. Okay, now we're good to go. I was getting surprised. Right. That is a terrible mistake there. Just like I realized it. And that's 6.4. We have the x-intercept, we have the y-intercept. We need one other point. So we have y being equals to a half x. Which point do we want to substitute? Let's substitute x equals to 1. If we substitute x equals to 1, a half to the power 1 is just a half. So these are the 3 points we're interested in. So let's sketch that. We just need our axes, the y-axis and the x-axis. So our points of interest, we have x-intercept doesn't exist, and then y-intercept is at 1, so we have a coordinate here. And then when x is equals to 1, like we are saying, y is equals to a half. So somewhere here we have our other point. And then our graph is going to look something like this. This is what we're going to have. We know that a half to the power x cannot be negative. So, we cannot go over that line. We need to stay above it. So there we go. That is the sketch of F inverse 6.4. Okay, let's just be a bit formal. This is x and this is y. This right here is y-intercept, so 0 and 1, and this right here is the other point, 1 and a half. Right, looks more clean. 6.5, determine the equation of the asymptote of g. Okay, so g, graph f and the asymptote of g, they intersect at b. So we can use f and the point b to find the asymptote of g. So f of x was and still is log of x with the base of half. So we want to substitute b of coordinates a half and q so that we can find the value of q. In doing that, we get q is equals to log of a half, the base is a half. This is equals to 1, and that is the asymptote of g. First principles, let's take a look. We have f of x, which is equals to 2 minus 3x squared, and it's supposed to find f prime of x. Well, using the power rule, we know full well that f prime of x should be equals to minus 6x. Okay, so when we use the first principle, we need to end up with this answer, minus 6x. If that is not the case, we have made a mistake somewhere on the way. So let's take a look. F prime of x should be equals to, using first principle, the limit as h tends to 0 of f of x plus h minus f of x, everything divided by h. So let's just calculate f of x plus h separately. We're going to have 2 minus 3, and then in place of x we have x plus h squared. So this is going to be equals to minus, well, not minus, but 2 minus 3, and then x squared plus 2xh plus h squared. So this is 2 minus 3x squared minus 6xh minus 3h squared. Okay, so we have f of x plus h. Let's minus f of x. So f of x plus h minus f of x. This is going to be equals to 2 minus 3x squared minus 6h minus 3h squared minus f of x. F of x is 2 minus 3x squared. Okay, so this is going to be equals to 2 minus 2. 2 minus 2 is 0. And then minus 3x squared minus 3x squared. So that's going to be plus. So look at this. 2 minus 2. That will give us 0. And then minus 3x squared minus 3x squared will give us 0. So we are left with 6xh minus 3h squared. Let's substitute back in our equation. So f prime of x, as the limit tends to 0, we have 6xh minus 3h squared. Everything divided by h. Let's take h as a common factor on the numerator. If we do that, we are left with 6x. Well, this is minus, right? This is minus, because take a look at this. Minus 6xh. So here we should have minus. So when you take a common factor, we're going to be left with minus 6x and then minus 3h divided by h. H and h will cancel out. Now let's let h be 0. We're going to have minus 6x minus 3 multiplied by 0. So this is just minus 6x. And it's exactly what we are saying, what we said we should end up with. So we are convinced that we have done everything the right way. That is 8.1. Quite easy to compute, 5 marks. And then 8.2.1, we're looking for f prime of x when f of x is equals to 2x to the power 4 minus 3x plus a squared. Okay, f prime of x is going to be equals to 4 multiplied by 2 is 8, and then 4 minus 1 is 3. Okay, and then 1 multiplied by minus 3 is minus 3, and then 1 minus 1 is 0. X to the power 0 is 1. So we are just left with minus 3. And then here we have a squared. A squared doesn't have a variable of x. So that's a constant. We're going to have 0. So f prime of x is equals to 8x to the power 3 minus 3. A squared becomes 0 because it is a constant. Or at least we're not derivating with respect to a. We're derivating with respect to x. So a squared will be 0 because of that. Right, that is 8.2.1. 8.2.2, we are looking for dx when we have 2x to the 3 minus square root of x divided by x. So instead of dividing by x, let's just multiply by x to the minus 1. Okay, we can do that. So dx, and then we have 2x to the 3 minus square root of x multiplied by x to the minus 1. Okay, so dx, and then what is 2x to the 3 multiplied by x to the minus 1? We're going to get 2x, and then we add the exponents. 3 plus minus 1, that is 2, and then minus x is the same as x to the power, well, square root of x is the same as x to the half, and then we're multiplying by minus 1. So this is going to be half plus minus 1, which is minus a half. Okay, so here we're going to have minus x to the power minus a half. Okay, and then now we can finally derivate. So we can introduce the equal sign. Okay, and then this is going to be 4x, we're just using the power rule, plus a half x, and then a half minus 1, that should be minus 1.5. So we have minus 3 over 2. And there we go. That is 8.2.2. 8.3. The following information is given for a function. F of 4 is equals to 5. So when x is equals to 4, y is equals to 5. And f prime of 4 is equals to 7. So the gradient at that point is 7. Determine the equation of the tangent of f at x is equals to 4 in the form y is equals to mx plus c. So this is quite an easy one. Y is equals to mx plus c. We already have the gradient. The gradient is 7 at that point at x is equals to 4. So we have 7x plus c. So we just need to see. We just need to determine c. But we're given this point when x is equals to 4, y is 5. So we have 5, 7 multiplied by 4 plus c. So let's take a look. 7, 14, 21, 28. So we have 28 plus c. So c is equals to minus 23. So y is equals to 7x minus 23. So let me just substitute 4 and see if I get 5, just to ensure that I'm not making a mistake. Y is equals to 7 multiplied by 5. 7 multiplied by 4 is 28. So multiplied by 5, it will be 35. Okay, so we have 35 minus 23. 7, 14, 28, 35. So 35 minus 23. So 35 minus 23, what is that? 35. Oh no, f of 4, not f of 5. I was getting surprised because I could see that it doesn't seem like it's gonna work out. So 7, 14, 28 minus 23, which is equal to 5. Okay, so this is fine.